You know how people always say that you should act normal, but I guess sometimes it's okay to not be normal and let our sample means be normal.
What?
In this video, we are going to understand Central Limit Theorem, and since it's the easy statistics video series up here, so we'll make it really easy to grab that. But before that, if you are not aware about random variables or what a normal distribution is, make sure to check out other videos in this playlist. My name is Rishabh and welcome to my channel. Let's get into this. So rather than jumping directly into the definition, we'll take a step backward and we're going to think backward in this one because that's what we actually do here at Amazon when we are trying to solve a problem. And by the way, if you want to check my Amazon interview experience, the link would be available in the icon above. So let's say we have a distribution. It could be of any kind. It could be a continuous distribution, discrete, random, what have you. And it has a mean, mu, and a standard deviation, sigma. Now let's say we take samples from the given distribution of sufficiently large size and compute the mean or the average for each sample taken. Now if we plot these averages, then the distribution of these averages would be a normal distribution with the mean same as the population mean mu and the standard deviation as sigma by root n, where n is the sample size. So the central limit theorem states exactly this. It says that if you have a population with mean mu and standard deviation sigma and you take sufficiently large random samples from the population with replacement, then the distribution of the samples will be approximately normally distributed. And if the population that we are taking the sample from is already normal, then the theorem holds true even for the sample smaller than 30. Nice, right? Yeah. But don't trust me if I say so. Let's see this with a Python example. Okay, so here I'm importing some libraries. I'm importing the NumPy library, Seaborn, Random, Matplotlib library for plotting, and some other things. So I'm going to just run this one. Here I am declaring a function that is going to plot the distribution for us. So let's just run this one. In this one, I'm generating a distribution that is so it's basically a random distribution of 1,000 random integers that are ranging from up until 1 from 1 to 1,000. So let's just run this one as well and let's see the distribution of this population. So as you can see, it's some kind of a random distribution. It basically looks a little bit like a flattened normal distribution, but it's basically generated from random integers, so it's a random distribution, we can say that. And now let's look at some statistics from this one. So the mean of this population distribution or the distribution X is 505 and the standard deviation of this one is around 286. Now let's just do what CLT says. So S underscore mean, this variable consists of the mean of 25 random samples and size of each of the sample is 30 up here. So we are generating 25 samples in total. Let's just run this one, and I'm also generating another variable up here. So this isn't explicitly mentioned by CLT, but this is one of the important things that you should keep in mind when working with CLT or something like that. So here, instead of computing the mean of each of the samples that we took, so unlike s underscore mean, we are generating a variable called s underscore std that would contain the standard deviation of each of the samples instead of the mean as in this case. So let's just run this one as well. And let's just plot this s underscore mean variable. Now, now according to CLT, we should see a normal distribution like distribution up here. Okay, it is on some level. So CLT basically says that it's approximately a normal distribution. This kind of approximation, I can agree with. So we definitely have kind of a normal distribution. So CLT is true, I would say. But let's just confirm it once by checking the statistics of this distribution as well. So here I'm computing the mean of this distribution that is shown above in this picture, and we are also computing the standard deviation of this distribution by using this formula. Let's just run this. So the mean of this one is around 488 and the standard deviation is 50. So if CLT holds true, this should be almost equal to what we have for the population distribution, and it's around 505. So I would say it's pretty close. It's not the exact one, but if you want a better results, you can definitely go ahead and increase the sample size up here. You can definitely go ahead and increase the number of samples as well, and you might see some better results. But yeah, I can go ahead with that. Now, let me just show you why in the first place I created this variable. So this variable s underscore std, this basically contains the standard deviation of 25 samples and each sample having 30 elements into it. So if I'm taking the average of this distribution, the standard deviation of the number that you are seeing, it's 280. Now, if you look at the standard deviation of the population distribution, it's 286. Pretty close, huh? So CLT also says that the average of means and the standard deviation of the sample will be equal to the mean and the standard deviation of the population that we have. I mean, this is one of the things that I have recently found. So now let's just see a few things to keep in mind when working with CLT. CLT is quite strong. No one has actually found a strong replacement of CLT, so that's why it's quite, quite strong and quite famous. Another thing is that the rule of thumb for choosing the sample size up here, it's basically 30. That's why I've chosen 30 up here. But if you have the original distribution like this one, if you have this as close to a normal distribution, then a sample size of 10 would be good as well. Another point why CLT is quite famous is that assume you're working on a real world data where you don't have any idea about the population or you don't have the complete data set, but you have a few samples from the complete population. Now, if you run CLT on those few samples and you see things like that, or the distribution follows a normal distribution, then you can assume things or you can estimate things about the population using the central limit theorem. That's how powerful it is. So now how do we validate this? I mean, it's giving the numbers close enough, but how do we solidify this? So that's kind of a thing that I have left out for another video. So the final video in the easy statistics playlist is going to be on hypothesis testing. We'll probably use this example as one of the examples in hypothesis testing, but we'll definitely look into other types of statistics tests that are basically used in hypothesis testing. So make sure you subscribe to the channel. I hope you like this content. If you did, hit a like, comment down on what you think about CLT, or if there's something that I've left out. And I'll see you guys in the next one. Bye bye.